So last time we did an introduction to axial loading for a very, very simple case in which we had a bar with uniform cross-section. So we just looked at a case in which we had a bar with a uniform cross-section, just a force applied at the end, and worked our way through to figure out how the deformation of the bar is connected to the force that you apply. And after a lot of work, and the work involved figuring out what is our convention for the reaction forces, and we put them positive with the coordinate axis, and we introduced a new quantity, which is our axial force resultant. And we said this is positive when the bar is in tension, so a positive axial force comes out of the cross-section. And in this case, just through equilibrium, we see that the axial force is equal to the applied end load N. And we introduce the measure of the deformation of the bar, which is the elongation of the bar. And then we introduce something that we call strain, axial strain, epsilon axial, which is the elongation per unit length. So something which is just a measure of how much really the material feels deformed inside this bar. So elongation for unit length. In this case, because the bar is uniform, then simply dividing the total elongation of the bar by the length of the bar gives us an idea of how much each part of the bar is deformed, because they're all deformed the same way. So if the whole bar elongates by delta, everybody feels the same kind of stretch. And so if you divide the total elongation by the length of the bar, you have a measure of how every little part of the bar feels. Then we said, we introduce also a normalized measure of loading, which is the stress, axial stress, which we obtained it by dividing the axial force by the cross-sectional area, with the same idea of the uniform strain, because this is a uniform bar, just one material. If it needs to carry an axial force N, every single part of the cross-section is going to distribute the load in the same way. So the load is going to be distributed evenly to every single part on the cross-section. So every single little area is going to have a load per unit area that's axial force divided by area. And then we introduce a very important concept, which is that the stress relates to the strain through a simple law, which is Hooke's law over here, which is linear in the special case of linear elastic material response. And this quantity here that relates stress to strain is called the Young's modulus, very important. And then by using all this information, we figured out that the relationship between the force that we apply to the bar and the elongation that we get is through some stiffness of the bar. So if the bar is stiff, you need a big force to obtain a certain elongation. And by using all those equations, we figured out that the stiffness of the bar, I can write it in terms of the geometry of the bar and the Young's modulus of the material. So that's what we did last time. So this time, so this is like grade school. This is like grade school for axial loading, and today we need to graduate to more complicated things. Because in general, in life, you do not just have a force at the end, and that's all what's going on, right? You can have forces applying along the bar at different spots. You may have distributed forces applied along the bar, not just concentrated loads. You may have a bar that changes cross-section. You may have a bar that's made of more than one material. Well, we want to get to the final destination, which is how do we relate what we see, how much the bar gets longer, or what's inside the bar, how much stress there is in the bar. And remember why we want stress? We want stress because the stress inside the bar controls if the bar is safe against failure or not. So we want to know what the stress is inside the bar. Because remember, high stress, like when I was poking my cheek with a pointy pencil, that hurts, okay? Hurts the structure. So we want to do all this for more complicated cases. Now, today, we're going to do this whole path of understanding all what's going on for bars in axial loading. And it's kind of like you make lasagna. Okay, I say that you have to make lasagna. And I come to you and I say, okay, just get your tomatoes, chop them up, start making tomato sauce. You're like, okay, I'm making tomato sauce. Then I come over and I say, okay, you start, I don't know, making the pasta on that side. Yeah, work the dough, just make it flat. And in the beginning, you do not know, like, what does the sauce have to do with the pasta you're doing on this side? And then I got you say, go grate the cheese, chop up your mozzarella and stuff like that. And it seems like everything is disconnected, right? And then I come to you and I'm like, start layering and putting the cheese and the sauce, and it starts looking good. You put it in the oven and you eat it, and it's good. And all this stuff is all together. And in the beginning, it all looks like different things, right? But then there is a story that comes together at the end. So today, we're going to make the lasagna of axial loading. So we're going to kind of start, and I tell you, make the sauce, make that. And you're like, what is all this stuff? We're going to introduce a lot of things. And then in the end, we're going to try to find how it all fits together, okay? So you're going to be patient. And what we do today for axial loading, we're going to do the same for torsion. We're going to do the same for bending. And by the time we're going to do torsion, you're going to say, I know she's making the sauce now. I know she's making the pasta now. And you kind of know where we are going. But today is the first time. So it's going to be like, how it will come together. It will come together. So we're going to start with one part of the story, which is loading. So what we did last time, we started talking about the axial force diagram. Okay, so the things that you did for homework were things that look like that. You have a bar, and along the bar, you may have maybe a force coming like this. So this is a 10 Newton force. And maybe here you have another force, which is 3 Newtons. And maybe at this spot, I have another force, which is, I don't know, 5 Newtons. And I asked you, figure out what is the force maybe at this section, the axial force at this section, right? Well, we can do this at every section. So if we do this at every section, what you build up by doing this is the axial force diagram, N of x. So that's a very important guide for our class. So how did we build it up? We said, okay, a good idea when you build your axial force diagram is to put it right underneath your structure, right underneath your bar, so that you can just make lines so that you can say, okay, so this is the end of the bar L, so this is where x is equal to L, and then maybe here, something happens here. You see a force is applied here. So bring it down, because something is going to happen here in your axial force diagram. So bring down your line from where the forces are applied. Boom, I bring it down here. And between this spot and this spot, nothing much is going on in terms of things changing for what the bar is feeling. So these are really the spot that we are interested in. So what do? You imagine that you cut right here, and you expose the cross-section of the bar here, and you put the end coming out, and you figure out what is the axial force in any spot between here and here. What do they feel? We can do the free body diagram, but you can kind of see it. If you were here, what do you feel? How much force do you feel? What do you think? Say that I'm here. So let's do the first one right carefully. So we cut here, and there is 10 Newton this way, 10 Newtons this way, and out of here comes your axial force N of x. You do not know. Once I cut this chunk here, you do not see the 3 Newtons. You see? You have no idea what's going on behind you. You're looking forward. You're looking forward, and if you cut in any point here, and you isolate this thing, for this to be in equilibrium, what is N of x? Bingo. So any place between here and here is going to have a level of axial load, which is 10 Newtons. Okay? Now I keep walking from left to right in my bar. I walk, I get here, past the point of application of the force. Now if I'm here, what do I feel? What do I feel here? Do I feel the whole 10 Newtons? No, what do I feel? I feel 7 Newtons because this guy is helping me. So any place I cut, all the way up to when I hit this other force, in any place in here, I'm going to have a load here, which is only 7 newtons. At this spot where I had a force of 3 newtons, my diagram went down exactly by 3 newtons. You see that? I stepped down, 3 newtons down right there. And then here nothing happens. And then here I have 5 more newtons applied to the bar. So if I'm in any spot here, what do I feel now? How much do I feel? I feel, so if I cut here and I take this whole, so when I cut, I look at this whole thing. And you imagine that you're there. You're just holding on the bar for dear life. You are the material inside here that holds on the bar there. How much do you need to hold? Exactly. You need to hold these, and this. You need to hold everything. So this n of x is going to come, make some more space. N of x is going to come up all the way up to 7 plus 5, 12. 12 newtons. See, I went up now. I went up by 5 newtons. I went up by 5 newtons because this thing adds to what I have to carry that way. You see? So this thing is my axial force diagram. Okay? So this is for concentrated load. For concentrated loads, you really want to make down the line where the loads are. So at the end of the bar, nothing happens. So in theory, if I want to go further, nothing happened here. I have no bar. Everything is at 0. I hit this 10 newtons. I go up by 10. Here I'm at 10. I hit this 3 newton going down. I go down by 3. I am at 7. I see these 5 newtons coming up. I go up. I am at 12, and I'm done with my axial force diagram. Okay? We good? What happens here at the support? You see I'm at 12. This is where the axial force diagram is right as you hit the wall. This has to do with what the reaction gives, right? So you see you have a positive axial force of 12 newtons. So the reaction force here must be holding back these 10 newtons. If I put the x coordinate, by the way, did you see that? Did you see any? I did not need to tell you which way x was in theory up to here. I just was doing the equilibrium. But to do Rx, I need to tell you which way the x is going. So if I want the reaction force here at the wall, if I have an axial force Nx of 12 newtons, that means the bar is pulling the wall that way. The wall needs to hold back with 12 newtons. So the Rx of A is going to be equal to minus 12 newtons. So Rx kind of brings you back down to 0. You see that? Okay, this is the first. Tell me again.
What is pulling back down to 0?
The Rxa. So in this case, Rxa is going to be equal to minus 12 newtons. If you do your calculations, right? If you do the free body diagram and you see how much is the Rxa. Remember, Rxa, see our blah, 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 conventions. If the x is going that way, Rxa is positive pushing. You see Rxa here cannot be pushing, must be pulling, right? So you're going to have a negative Rxa. And in a way, Rxa, you can think, so Rxa is pulling that way. So you see when you have a load that pulls that way, you go down. So your Rxa kind of brings you back down on this side, if you want. So I'm just saying this to help with intuition. But you calculate this diagram using your sum of fx equilibrium, right? But then when you want to look at it and say, does it make sense? Does this load make sense? You kind of walk your diagram from right to left and see if it makes sense. Yes?
So if you set x to go that way,
yes.
Would you put the arrow up?
If I said, so let's do it. Let's do it, right? I could have put my x-axis going the opposite way. Okay, so if instead of putting my axis that way, say that I put the axis that way. Okay, boom, boom, boom. That's a very good question, by the way. I really appreciate it. If you ask me, this kind of things helps. So I put the axis this way. This is my x-axis. The wall is still here. I did not move the wall. My wall is still on the left. But my x-axis now points from left to right, okay? As I walk through the bar, if this section here feels pulled or pushed, does it matter which way x goes? No. If I'm here, if I take this section here, I still have this equilibrium, this free body diagram here. On this section, I'm still pulled by 10 newtons. So if I do my n of x, so now my n of x is like that. If I do my n of x like this, walking like this is still going to be 10 newtons. This is still going to be 7 newtons. This is still going to be 12 newtons. And now, the reaction force at A, when I do the free body diagram, and I do the bar like that, and I draw the reaction force at A, I'm gonna write it like that, Rxa, right? Because my x points that way. When I do the equilibrium for Rxa, I have 10, I have 3, I have 5, and guess what? What is going to be my Rxa? It's going to be plus 12 newtons, right? It's still going to work out because the solution is still going to tell me that at the wall is pulling me this way, okay? So your x-axis only, it's only useful for you to do your algebra to make sure that your solution comes out right and everything is right. The physics stays the same, okay? Are we good with this? We're going to do so much of this that things are going to work out. Yes, tell me.
But it doesn't matter, like, you don't mess with the sign on the n of x, right?
The n, exactly. You don't mess with the sign of n. Never mess with the sign of n. N doesn't like to be messed with.
So really the positive negative is just a direction indicator.
The positive or negative is like if you have an x-axis and you're finding the Cartesian x component of a force. You know, if it's positive or negative, given the direction of the force, depends on which way the axis point, because that's a Cartesian component. What the n is, if it's positive or negative, has to do with does the bar feel pulled or does the bar feel pushed? Couldn't care less if it is, you know, the x direction points left or right. You don't mess with the signs of n. Very good sentence, okay? Don't mess with n. We good? Okie dokie. So let's do something a little more challenging. That is, we're going to deal now with distributed loads. So that was concentrated load. Now we're going to do distributed load. So distributed loads means I don't just go there and apply a concentrated force. I just do a little bit at a time. So a distributed load, we're going to write this as Fx of x. And what this means is that I'm applying a force. So the units of Fx of x are going to be force per unit length, so say Newton per meters. So just to set an idea, just to set our example, we can imagine that we have a bar and say that my bar is of length L. And then on this left side of the bar, nothing happens. But on the right side of the bar, so on the half of the bar here, I am just applying a distributed load, right? So it's kind of like I'm just going like that and pulling, but I'm pulling everywhere. You see what I mean as distributed load? Okay, so let's say that, so our Fx of x, let's define it as 0 for 0 less than x less than L over 2. And then let's say that over here, just to make life easy, I have a constant distributed load F0 per unit length. So on that side is going to be F0. And let's make it that is 2 newtons per meter. You see, I go here and I give it 2 newtons per meter, pulling along the x-axis. So now I need an x-axis because, see, Fx is going to be positive if it goes with the x-axis. It's going to be negative if it goes against the x-axis. Okay? So that's my Cartesian component of my distributed load along the x direction. So let's say that I have 2 newtons per meter on this section for L over 2 less than x less than L. And that's my distributed load. So what I want to find out I want n of x. Okay? So it is useful for this kind of problems to make yourself a plot of f of x. In this case, it's really, really easy, but I'll do it anyway. So I do fx of x is going to be equal to, and always like draw your lines down from the structure. So that's your structure. Draw your lines down along the x-axis, and your f of x then is 0 from here to here, and then from this section here is constant equal to f0. Okay? So that's your diagram for f of x. By the way, if I ask you what is the resultant load for that? If I ask you right now, without giving you anything else, what is the resultant load that comes from the distributed load? Can you tell me? Can you tell me?
L.
You need L. You need L to tell me how much load I have. Because I just told you I have 2 newtons per meter, but I didn't tell you how long the bar is. But now say that I tell you that the bar is 4 meters. So how much load do I have total? 4 newtons. Exactly right. So the resultant load is going to be F0 times L over 2, and that's going to give us 4 newtons. Okay? Okay, but I do not want just the resultant. I want to know what every single section here of the bar feels, not just how much the total load is. So what do is I use the same method as we did here. We cut, right? So if this is the bar, I'm going to draw it up here just so that we can get our geometry right. This is the bar, and I have F0 on this side of the bar. The first thing that I do a cut number 1. So where do I cut? I cut in a way that isolates things that happen in a different way in different parts of the bar. So I can see here already that it's going to be different if I cut in this section here, which is where I have the load, or this section here, which is where I don't have the load. So I can see already that I need to do at least a couple of cuts to figure things out. You see that? All right, so let's do our first cut. So let's do the first cut right here. So this is our cut number 1 that we're going to do for x greater. So let's do L over 2 less than x less than L. So if we cut here and we have this little bar left over, and remember, this always goes all the way up to L. So I'm cutting at an x. Let's call it x1, because this is our first cut. So we cut at a certain distance from the bar x1, which is bigger than L over 2, but less than L. And here is what I see. I see that I have a bar with an F0 on top. And where I've cut, what do I expose there? Who is coming out of this guy? N. And which N? N of x1. Because this is the axial force that is inside the bar at this x1. OK? Good?
Is it relative to L over 2 or from the wall?
And N of x1 is how much. So x, the coordinate x-axis starts at the wall. So if I go to x1, this is my first cut. I'm a distance x1 from the wall. Okay? And as I cut at x1, I expose what is the axial force at x1. And because it acts at this section here, I call it the axial force N at x1. Is the notation OK? OK. So how do I find N of x1? Well, I put this guy in equilibrium. So if I cut here, I do N of x1. Well, I do sum of the forces x. Oops. I do sum of the forces x equal to 0. And that's equal to, now remember, the x-axis goes that way. Is this positive or negative? Brilliant. Minus n of x1. And then I have what this guy is doing. This load is F0 per unit length. So each little slice here, so if I take a slice here, dx prime, and I do dx prime, and you already know that if I'm putting the prime, you're going to get into integrals, right? Because this is my variable of integration. My variable of integration is going to go from x1 all the way to L, right? But if I have a slice dx prime with a distributed load F0, that slice itself is going to give me a load F0 dx prime. But then I need to sum it up from here all the way to L. So I need to integrate this thing going from x1 to L, F0 of dx prime.
Should that be a plus sign between?
Oh, yes. Thank you. That's an ugly plus, but it's a plus indeed. Because it's a plus because F0 is positive. So when I project it on the x-axis, it's going to have a plus. Thank you so much. OK, we good? Excellent. So this is an easy integral. So I can say this is equal to, actually, let's directly get n of x1. So n of x1 is going to be equal to, I bring it on the other side, so it's going to be equal to F0 x prime integrated between x1 and L. And you think, are we back in high school? Do you think I cannot do this stupid integral without having to do the brackets and bottom and top and everything else? I don't know. I see that a lot of these problems that the errors that I see a lot of time is because people forget to put the bounds of integration. So when I do it on the board, I'm going to write it this way so that you remember that this is an integral. It's not an indefinite integral. This is something that tells you where to start and where to end, and you better remember it, right? Because if I write it like that, then you can see that this is equal to F0 that multiplies L minus X1. OK? Are we good? So these are important. If we do it on, so this is it. This is what n of x1 is going to be. And this is going to be true for any x1, which is between L over 2 and L. It's not a big surprise, because, of course, how much x1 needs to carry is the distributed load multiplied by the length over which the load acts, which is L minus x1. So it makes sense. But for more complicated forms of f of x, sometimes you may want to actually set up the integral like we did and solve it carefully. So this is the first cut. The second cut is going to be even easier. So our cut 2 is going to be here. When we do cut 2, we have this part here of the bar, which has the distributed load. Out of here, so this is now, this x here is x2. Out of this thing comes out n of x2. And now I can play the same game. How do I find n of x2? This is at x2, this is at L over 2, and this is at L, right? So when I do the sum of the forces x over 0, sum of the forces x equal to 0, what do I get? I get minus n of x2 plus the integral from x2 to L of f of x in dx. And that one I need to split. I need to split because fx is 0 from x2 to L over 2, and is f0 from L over 2 to L. So in order to find n of x2, I need to split this integral. So I get n of x2 is going to be equal to the integral from x2 to L over 2 of 0 in dx, which guess what is going to be 0, plus the integral from L over 2 to L of f0 dx. OK? So same things that we did here. We get 0 plus f0 that multiplies x between L and L over 2 and L. And I know I should do it, but I'm not going to do it, because that is L minus L over 2. So that's L over 2. OK? So that is the cut number 2. And this is for 0 less than x2 less than L over 2. So how did we figure out our n of x? N of x is going to have 2 parts. So let's summarize over here. Right? Let's do our diagram. Just underneath there, just continue the line. And here you put n of x. N of x is going to have, I carry down. So our n of x is going to be equal to this thing if x is less than L over 2. So if f0 L over 2 for 0 less than x less than L over 2, and is going to be equal to f0 that multiplies L minus x for for L over 2 less than x less than L. So if we plot this thing out, what do we find? We find that on this side of the bar, we find that n of x is f0 L over 2. On this side of the bar, we see that n of x is linear. You see, it's linear with x. Of course, for x equal L over 2, you find the same thing that you have here. Why do you find the same thing? Because there is no concentrated load. There is no concentrated load at L over 2. The only time your n of x diagram jumps if you have concentrated loads. Concentrated load make the axial load jump. They don't like to jump. Nobody likes to jump. I don't like to jump. So there is no reason to jump here. And indeed, it doesn't jump. At x equal L over 2, you still have f0 L over 2. For x equal to L, you see I get 0. So I know that this one is going to be linear, so it's going to look like that. So my f of x, my n of x, does that. Great. This is it. This is what you need to do to get the axial force diagram for distributed loads. Now, I want you to notice something kind of cool. Are we good with this before I tell you the really cool thing? Yes?
You might ask this earlier, but so x1 is only from L2 to where the cut is, right?
x1 is any x. So x1 is just a generic x that happens to be between L over 2 and L. Any position I choose between those two bounds is going to give me the same equations. Thank you. We good? We good? OK. So what is the cool thing? Look at this diagram and look at this diagram. Where f of x is nothing, n of x is constant. See that? Now, f of x is constant, n of x is linear. Any bells? Some integrals, derivatives, some things, right? I mean, of course, it makes sense, because if you think about how we get n of x from f, we integrate, right? So it makes a lot of sense that if we have if we want to go the opposite way, if I write dn dx, this is equal to something related to f, right? So what is dn dx between here and here? Zilch. What is dn dx from here to here? Minus f0. And f0 used to be, it is our f of x. So dn dx is simply equal to minus fx of x. This is really a useful kind of thing. It's useful either if you like integration, because you can just use this relationship given fx of x to integrate and find n of x, right? Which is the same thing as what we did over here by starting from there. And it's also cool because it gives you a quick way to make sure that after you build your old diagram with doing all the equilibrium stuff, you look at the diagram and say, does this work? And if it doesn't work, you better go back to your algebra because you made some mistake someplace. Okay, so that's a very useful thing that you can use to verify that your axial force diagrams are correct. Okay, where does this come from? It simply comes from the equilibrium of a slice. It's not like magic. If I take a slice of thickness dx, and so that this one is x, and this is x plus dx, so out of here comes n of x, out of here comes n of x plus dx, and if I put equilibrium, then I get the same thing. I find n of x plus dx minus n of x. And now here I have a distributed load fx of x on these things is going to be equal to minus, because this sums again, minus fx in dx. And so if you take this thing, you substitute it, you get the same thing as this. Okay, so it's not magic, it's just equilibrium of each slice. Useful relationship to make sure your force diagrams are correct. Good? We made the sauce, okay? So